both parts of this experiment. Alright, scholars, so I've done quite a bit of work here to set up what we're going to need for experiment A. I've got before the collision, importantly, we had that mass 2 was stationary, and we also had, we ended up pushing mass 1 towards mass 2. So actually, one of the helpful things about mass 2 being stationary ahead of time was that we already know its velocity was 0. So I pushed the cart, it smashed into it, and then they hit and stuck together. What's important here is that the masses are stuck together, so they actually have one mutual final velocity, which is something we don't yet know, but we'll be able to get it from the data we collected. Now, I showed in the slides a moment ago that we have the masses of our two carts. Somewhat interestingly, they have very, very nearly the same mass within a few grams of one another. That's not that surprising since they're almost identical carts anyway. I've also written down other data that we're going to need to know and going to have to measure from our experiment. So we need to know the initial velocity of mass 1. We already know the initial velocity of mass 2. And then, maybe surprisingly, again, they have a mutual shared final velocity because they're stuck together. So here is our linear momentum equation. We've got the momentum of the first cart, the momentum of the second cart. Both of these are before the collision, and then we've got the momenta after the collision. So if you don't yet have this down, make sure you take it down, and we'll proceed from here. Alright, so here is the data that I collected. If you're using the data file, this is the one called empty carts, hit and stick. Notice I've got the position of the green cart from the video, that was the one I pushed, and the position of the yellow cart. That was the one that was originally stationary. Now I'm not sure why, but this changed colors on me. That's okay. So again, this is the cart that was sitting, 45 centimeters from the end, just sitting and waiting. This is the cart that I pushed. So take a look. What we can do is we can find the velocity beforehand by taking the slope of this line just the moment before it hits. Remember, we can do that in a couple of ways. Perhaps the easiest way is to use the tangent tool. We want to get that as close as we can before we see it change at the collision site. So we want to go for somewhere in that neighborhood. In a moment we'll switch to the velocity. So it looks like it was about 0.5 meter per second. We'll get the precise value in just a moment. Now what's kind of cool about this is once they hit and stick together, we should see these two slopes become identical because they're stuck together. So watch this. Once they hit and stick, with a tiny bit of variation because of some errors in measurement, notice the slopes are essentially identical with one another as we move forward. Now they begin to slow down because of the effects of friction, so we actually want to look at the speed immediately after the collision once they're properly stuck together, and you can see it's around 0.25, around half of what it was before the collision. I want to show that to you in terms of velocity as well, and then we'll pull the data and actually solve the problem. Let's turn off our tangent tool, and instead of position, let's go with the velocity of both the green and yellow carts. That looks good. So this graph looks very different. Without having seen the video, I think it would be really tricky to explain what was going on. So this is the cart that I pushed. Notice this is me pushing it, and then it slowed down a little bit because of friction, not too bad. And what we want is we just want the velocity this moment before the collision. Notice it slowed down very abruptly over a short period of time, about 0.2 of a second, and this cart was at rest and sped up. I know this is a little tricky to see because you're not actually playing around with these carts, but again, the two values we need to know are the velocity before and after the collision. I'll just show you again. We want to know the initial velocity of the green cart, this one back here, and we want to know their velocities after they collide. So let's do that. I'm just going to actually use the regular tool here. So let's pick this value. It's just before it starts to dive down. This should be just about perfect. So 0.515 meters per second. We'll jot that down. So our initial velocity of the first cart is 0. Oops, I'll do that in black. 0.515. I ran out of room there. Meters per second. That's fine. and then let's find their mutual shared velocity after the collision. I'm going to pick right here after it starts to level out. So 2, 4, let's go 2, 4, and we'll round to 0.25 meters per second. I know I'm kind of truncating some of my values there. Let's go 0.2. Yeah, let's just round it and call it 5 meters per second. So there you can see we've got our final shared velocity of the two. Now keep in mind, we might be just a tiny bit off. But what we're going to do now is plug in all this information and see if this side of the equation is exactly equal to this side or very close. So now, if I'm not going to draw it, but you could put a line here. This is just a regular physics problem. We're given the masses, we're given some data, and we have a little bit of context about the situation. That's going to help us solve this problem. So first things first, the initial velocity of this one is 0. So we can say that this entire term, this is really nice, goes away. I'm going to rewrite it in just a moment, but I also want to combine these two masses. They're actually stuck together. So since they have a shared velocity, I can replace both velocities with just v final, and then I can factor out one or the m's. I'll show you what that looks like now. Alright, so because the first cart was the only thing moving in the beginning, it had all of the momentum at the start. These other two carts are, or rather after the collision, the carts are stuck together. So you can think of this as the combined mass of the two carts stuck together, which is just going to be the sum of these. And then the momentum after the collision is just going to be their shared mass times their shared velocity. Pretty straightforward. So now let's plug in the values and see if the momentum before the collision is equal to the momentum after the. So I've plugged in my values for mass, initial velocity of the first cart. Their mutual masses are added together times their final velocity. So the left-hand side, I calculated a total initial momentum, which should be the total momentum throughout the entire process, is 0.145 kilograms meters per second. And the question is that equal to the final momentum after the collision? See if you can do the calculation and check it out. So when you do the second calculation, you get 0.141 kilograms meters per second. Those are very close. We don't see a difference until the tens, hundred, thousandths place. Now we can calculate the percent difference between those two numbers, and it's a little bit more complicated than finding percent error because we don't actually know the accepted value. All that is to say, the way you'd calculate the percent difference is you would take the final momentum minus the initial momentum divided by the average of the two. What we're assuming here, which is maybe an okay assumption, is the true total momentum of the system is somewhere between these two numbers, or the average. If we take the average of those, that's actually pretty easy. It's just 143. So we would do 141. We'll take the absolute value of this too and multiply it by 100. Yeah, that works. So 141 minus 145, that's 4, divided by 143. That would be the average of those two numbers. We take that and multiply it by 100%. I got something like 2.8% difference. Now, I know we haven't done a lot of experiments during all of this virtual learning, but that is darn close. That is a really good experiment, and we just kind of roughly picked one. If we were going to do a full precise experiment of this, we would do many trials, and we would end up averaging the percent difference over many trials. Remember, we had to make a couple of judgment calls about exactly which velocity to pick. We did a little bit of rounding here and there. So for example, if I had picked this velocity, which is a little bit smaller, it would have made this momentum smaller, which would have made the whole thing even that much closer. So this is a darn good experiment. Now you might ask, maybe we really did lose some momentum. Where might it have gone? Keep in mind, all we're able to measure here is the straight line back and forth momentum of these carts. So if during the collision the carts went up or down or side to side, in any way, some of that momentum would have been lost to going in a dimension that's not linear, not straight back and forth. So all things considered, we can be pretty satisfied that this is a demonstration of the conservation of momentum. Just a quick reminder, we wanted to also take a look at the elasticity of the collision. Before we do that, did we show that the momentum was conserved? Yeah, we did, to within about 2% or 3%, which is a pretty reasonable one with the margin of error in this experiment. So anyway, with that in mind, let's calculate the elasticity of the collision. So all we have to do for that is take the total kinetic energy before the collision and the total kinetic energy after and divide. It'll end up being something like a fraction. Now, here we can't really take the average because we don't actually know. It's kind of hard to compare apples to apples here. So we'll just get a rough idea of the elasticity of this collision. So we want to measure the elasticity. All we need to do again is take the kinetic energy after divided by the kinetic energy before. Now we're looking at the total energy in the system. So the kinetic energy before the collision would be the sum of the two energies. Now, lucky for us, the second cart was sitting still, and the for the after kinetic energy, the two masses are actually stuck together with a mutual velocity. So we actually have quite a bit less calculating to do here. So I'll take the data from our last part of the experiment, and we'll plug it in for the mass and speed, and we'll check our results. Alright, so I've plugged in my information, and I'll jot down what I got for the kinetic energy both before and after. Before, I got 0.037, we'll round to 3 joules, or I guess that would be 37.3 millijoules. And then for our after, I got 0.017, we'll round that up to a 7 joules, or you could call that 17.6 millijoules. So notice we lost just a little bit. Well, let's actually see how much we lost. So we'll look at the elasticity, and it's just a ratio of how much you have. So we'll go 17.6 millijoules. Keep in mind you could use any unit there because they're going to end up canceling. It's just a ratio over 37.3 millijoules. And we end up with 17.6 divided by 37.3. We end up with 47% elastic. So we lost just a little bit more than half. So you could also say that this is a 53% inelastic collision. But the important thing to note is, and then we'll summarize it here, we lost 53% of the original kinetic energy. See, there you have it, folks. That is the elasticity of this collision. Now, it entirely depends on the situation that you're looking at. So, for example, if we increase the mass of the moving cart or the initial stationary cart, it's very likely we're going to get a different measure of elasticity. To just briefly wrap this up, I want to show you a different type of collision that you folks are also going to take a look at. So here we have a classic hit and bounce collision. It is either going to be more or less elastic. We'll see in just a moment what you think it might be. So in this case, our carts have these little plungers on them. So instead of hitting and sticking with the Velcro, now they're going to hit and bounce, hence the name hit and bounce. So check it out. So we don't really care about that second collision there. What we care most about is this first collision here. So notice they don't hit and stick together, which means we're going to have to collect data in a slightly different way. Here's what it looks like on graphical analysis. So there you can see the slope of the green one, or rather the yellow one, is a little steeper than that of the blue one. It's moving much more quickly after the collision than the other one. So we will take a look at how elastic this one was, and then we can also do versions of the experiment where we add mass to the first cart add mass to the second cart, different kind of combinations like that. So there you have it, folks. That is everything we need to know so far about momentum and collisions. Thanks so much.